All right, so we've talked about the extreme cases of perfect competition and monopoly, and the goal, this lecture and sort of how I motivated game theory was we want to think about what happens outside of those extreme cases. So in a case in between where we have a handful of firms, but not an infinite number and not one, right? And what we're going to see there in those cases is strategic interdependence in the sense that what one firm does affects the other firm. So the price that Chick-fil-A charges, right, affects the demand for Zaxby and so on and so forth. Um, so we're going to study three different models that try to take this into account. The first model that we're going to study is Cournot competition, or the Cournot model. And this is a model of quantity competition. So like we had firms compete, like in our monopoly model, firms were choosing quantity, right? That's going to be the same here. Firms are going to be choosing quantity. Now you might not like that assumption, because in real life it often seems like firms are choosing price. Or we see, like the gas station lists its prices, right? The grocery store lists its prices. Amazon, like when you go online, like they're listing prices. And so you might want to think about firms competing on prices, which is the Bertrand model. And what we'll see with the Bertrand model is that it's very weird and that prices basically get bid down to perfect competition very quickly. And so it's not especially realistic, but it does get us to start thinking about how we can have firms competing on price, which you may like as just thinking about how does the model describe the world. And I want to note that both of these frameworks assume homogeneous products. All right. Now, one way that we can get around this issue with Bertrand competition of how price gets bid down very quickly is we can bring in product differentiation, and that's going to be the Hotelling model. And so, at least in the way that I'm going to teach it, the Hotelling model also has some location choice stuff going on that we're not going to worry about here. But I'm going to teach it as a differentiated product price competition model. All right, so it's going to be price competition, which will be similar to Bertrand, right? But we'll have product differentiation, which is going to allow us to get around some of the issues in the Bertrand model. Having said that, I'm going to talk about this. You will not be tested on the Hotelling model. It's complicated, and I don't think that other faculty will expect you to know it when if they ever talk about it. But it's something that if I just left you with Bertrand and said this doesn't work very well, I think you'd be a little bit annoyed. So I want to sort of just finish off that thought, but it's not something that I think. I think that with an undergrad econ major, you're sort of expected to know Cournot and Bertrand. I don't think Hotelling is something that you're necessarily supposed to be aware of. But I think it sort of helps me finish my story. All right, so I'm going to talk about the Cournot model. So Cournot model is a model of homogeneous products. And it's quantity competition. All right, so we've talked a lot in this class about, what does it mean for firms to compete in quantity, and just to, this might not be the most sort of, I think in many senses, feel like the most realistic model, but one, we'll see that it in some ways does a much better job than sort of the naive price competition model that we'll talk about in a few videos. But also there are some markets where this actually might be a decent approximation, where if we, commodities like corn or oil, it's not uncommon to hear, people talk about, firms setting quantities, or, the quantity really pushing market price, right? So like OPEC right now, there's big discussions about how much each country is going to produce. Right, and we can think of that as quantity competition across countries, okay? So the actual assumption here, it's not just that firms are quantity setting, but the assumption underlying the Cournot model is that all firms choose their production simultaneously. And without really communicating with, other firms. All right, and if you want to sort of get away from this assumption, right, you can look at the Stackelberg notes later on and sort of see where that matters. And I'll probably talk about it in the notes as I go through. So then, once each firm has chosen their production, firms bring their products to the market. And the market price is the one which sets aggregate supply equal to aggregate demand. All right, and the big part about this assumption, right, that firms choose their production simultaneously, right, this implies that firms have to think about what other firms are going to do, okay? So firms plan their production based on their beliefs about their rivals' quantity choices. Right, and what this suggests, right, is that each firm, right, or what we're going to need to do is find a Nash equilibrium of this game, right? Each firm is going to make their best response, right, to what they think the other firms are going to be doing, right, and they're going to be believing that the other firms are going to be best responding to them. All right, so the way that we solve Cournot first, we're going to find each firm's best response function. And I'm just going to say BR for best response. All right. And then the Nash equilibrium, I'm going to say NE for Nash equilibrium, is the outcome where each firm plays a best response to the other's best response. All right, simple enough, right? It's just standard Nash equilibrium. So let's go through an example here. This is just, we're just going to go with a two-firm case, so two firms, homogeneous product that they're selling, and we're going to say that they have marginal costs. Actually, let's do it this way. Let's say that cost is equal to 2Q. All right. And the demand in the market is PQ is equal to 5 minus Q. Okay, so we're in a world that has multiple firms. And so before, right, we had like a single firm, we did little q, and big firm we did, or with monopoly, right, or aggregate demand, we did big Q. So I just want to make that distinction clear again. Q is market, supply or demand, in this case supply, right? Little q is firm supply. All right. So in this case, because there are two firms, big Q is going to be equal to Q1 plus Q2. Okay, so the thing that we're going to be asked to do is let's find the equilibrium price and quantity. Okay, and before solving through this for the Cournot game, I think it's probably instructive just to think about what would happen under monopoly and under perfect competition. So under perfect competition, well, we have a marginal cost of 2. So PC, let me call this P comp, is equal to 2, right? Which means that the quantity sold in the market is going to be equal to 3 because we've just, due to demand, right? If the price is 2, quantity has to be 3. Under monopoly, this takes a little bit more work to get, but the quantity, the monopolist quantity would be 1.5. And again, let me do it this way. And the price in monopoly would be then 3.5. All right. Okay. So now let's go through and actually solve out the Cournot duopolist problem. So the first thing that we want to do is we want to find each firm's best response function. And to do that, right, what we're going to do is find, let's say, firm 1's best response, which we'll call Q1 star, as a function of Q2, right? Assuming some arbitrary output for firm 2, just Q2. All right, so firm 1 thinks that firm 2 is going to produce Q2, right? And then what's firm 1's best response to that? Okay. So the first thing that we need to do, right? So firm 1 thinks it knows how much firm 2 is going to produce. So then what do? Well, like always, how do we find firm 1's best response? Right, we're going to write down the profit function and then take a first order condition. Right, we've been doing this a whole lot. Okay, so in this case, right, the profit function is a function of Q1 and Q2, all right, and it's just revenue, right, which is the market price, right, times Q1, how much firm 1 sells, right, minus firm 1's costs. And it's important to note, right, price, right, depends on Q1 plus Q2. Right? So if Saudi Arabia produces a whole lot more oil, that's going to lower the price that Russia can get, right? Or it's going to lower the price that the US can get. And that's why they care, right? Because, so the quantity or the price depends on the quantity that the other firm produces, right? Revenue is just price times cost, or times quantity, and then minus cost, which is just a function of what that firm or firm 1 makes. So quantity and costs are firm specific. All right, so now, and I'm going to just go through this kind of slowly. What we're going to do is we're going to plug in what we know, which are these two functions. So this is 5 minus Q times Q1 minus 2Q1. That's just plugging in the demand curve and the cost curve. 5 minus Q is 5 minus Q1 minus Q2, right? Because Q is just Q1 plus Q2. This is all times Q1 minus 2Q1, or 5Q1 minus Q1 squared minus Q1 times Q2 minus 2Q1, or 3Q1 minus Q1 squared minus Q1 times Q2. Okay, so this is our profit function, and then we're going to take a first order condition. All right, so we want to find the point where this derivative of the profit function is equal to 0. So we take the derivative, which is with respect to Q1, and so that's going to be 3 minus 2Q1 minus Q2 is equal, and set it equal to 0, and then solve for Q1. All right, and so we get 3 minus Q2 is equal to 2Q1, or Q1 star is equal to 3 minus Q2 over 2. All right, and I'm just going to write it this way, 3 over 2 minus Q2 over 2. Okay. So this is firm 1's best response function. Right. So no matter what quantity, right, firm 2 decides on, right, this tells you what the best thing it is for firm 1 to do. Okay. So if firm 2 decides to choose, may produce 1 unit of output, right, firm 1's best response would then be to produce 1 unit of output. If firm 2 decides to produce 2 units of output, firm 1 should produce a half unit of output, right? But what this tells us, right, is basically, you know, this is firm 1's best response to whatever they think firm 2 will do. All right, so I'm going to do a little trick here, and it's a trick that you can use too throughout the class. Is let's just assume that the firms are symmetric. Okay, they have the same costs, and they have the same profit function. So if you were to go and work through it, you'd find the same thing. But I'm just going to impose symmetry to save some time here. So here we have Q2 star is equal to 3 over 2 minus Q1 over 2. Okay. So now I have both firms' best response functions, right? And then what we want to do, right, is find a Nash equilibrium. And remember, a Nash equilibrium, right, is just when both firms are playing a best response to the other's best response. So what we're going to do is find the Nash equilibrium by combining best response functions. Right, if I say that, you know, firm 1 has some conjecture about what firm 2 will do, and their conjecture is that firm 2 is going to play their best response, right, to firm 1, right, then we can just plug that in here and then solve out for what would be the outcome. All right, so Q1 is equal to 3 over 2 minus 1/2, right, times Q2, which is just 3 over 2 minus, I'm just going to call this 1/2 times Q1. All right, so that this term here got plugged in here, right? So this becomes 3 over 2 minus 3 over 4 minus plus 1 over 4 times Q1. Right. We're going to subtract 1 over 4 times Q1 from both sides. And so we're going to get 3 over 4 Q1 is equal to 3 over 2 minus 3 over 4, which is 3 over 4. All right. Multiplying both sides by 4 over 3, we get Q1 star is equal to 1. Okay. So all we've done is just taken Q1, right, from above, plugged Q2 into it, and then solved for Q1. Okay, so this is really just algebra. And what we got is that firm 1 should produce 1 unit of output. We can plug that back into here, right, and we'll see that also Q2 is equal to 1. Right, so 3 halves minus 1/2 is just 2 halves, or 1. Right, so the quantity in the market, right, aggregate supply is 2, and the price is equal to 5 minus Q, which is then equal to 3. right? What we did is we got aggregate quantity by just summing up Q1 and Q2, and then we got the price by plugging in the quantity into the demand curve, the same way we did with Monopoly. So the one thing that I want to point out here, and we'll talk about this after we do a handout, right, is that before, right, when I made just like a quick note that of the perfect competition outcome and the Monopoly outcome, right? And what you'll notice is that we're somewhere in between, all right? So under perfect competition, right, quantity was 3, right? Now under Cournot, quantity is 2, under Monopoly was 1.5. We're somewhere in the middle. Same with price, right? Under perfect competition, it was 2. Cournot, it's 3. Monopoly is 3.5. We're somewhere in the middle. Okay, so now I'm going to go through, or if we were doing this in class, we would do handout, it's called H13 Cournot competition. .pdf. All right, so now I'm going to do handout H13 Cournot. And in this handout, we have an inverse demand curve of 12 minus 2Q, where capital Q is just Q1 plus Q2. It's always going to be that. And each firm has a cost curve. C is equal to 4Q. Right, and the goal is going to be to find the pricing equilibrium price and quantity. Okay, so the first thing that we're going to do, right, is we want to find each firm's best response function. And how do we do that? All right, well, what we're going to do, right, is, well, what this is asking is basically, what is the most profitable quantity given some arbitrary quantity the other firm produces? So we're just going to write down the profit function. For firm 1, let's say. All right, so pi 1, and this is again going to be equal to revenue, which is PQ times Q1 minus C of Q1, right, which in this case is going to be equal to 12 minus 2, and I'm going to skip a step here and say Q1 plus Q2, but that's just coming from the fact that Q is equal to Q1 plus Q2. Right, and all of this in parentheses here are important, is multiplied by Q1. Right, so this is the demand curve, right? Inverse demand curve multiplied by Q1 minus 4Q1. All right, and now I'm just going to do a bunch of algebra to get sort of like terms together. So this is going to be 12Q1 minus 2Q1 squared minus 2 times Q1 times Q2 minus 4Q1. I'm going to subtract the Q1's terms, and we're going to get 8Q1 minus 2Q1 squared minus 2Q1 times Q2. And then what do? We have our profit function. We're going to take a first order condition. All right, so the first order condition here, the derivative of this with respect to Q1 is just 8 minus 4Q1 minus 2Q2, set that equal to 0. All right, and then from there, we're just going to solve for Q1. And so we're going to get 8 minus 2q2 is equal to 4q1, or q1 star is equal to 2 minus 1/2 times q2. All right, this is our best response function. Right, for any q2, this tells us the optimal q1. Right, this tells us the profit maximizing quantity for firm 1. Again, I'm just going to impose symmetry. You could do this again for firm 2, and solve out for firm 2's best response function. I'm just going to impose symmetry. You should just get used to doing this too. If we had different cost functions, or if we were playing Stackelberg where they respond to each other, you wouldn't want to do this, but we're not doing either of those in this semester, so we have firm 2's best response function, right? And then the thing that we want to do, right, we have each firm's best response, then we're going to find the Nash equilibrium. Out a little bit. Find the Nash equilibrium by plugging each firm's best response into each other. Right, a Nash equilibrium is just one firm playing its best response to the other firm's best response. So to do that, let's take Q1's best response, or firm 1's best response, and that's equal to 2 minus 1/2 times Q2, where for Q2 I'm going to plug in 2 minus 1/2 Q1. All right, and then we're just going to solve for Q1. So this is just algebra from here, which is 2 minus 1 plus 1/4 Q1. So we're going to get 3/4 Q1 is equal to 1. So Q1 is equal to 4/3. And then if you plug this back in to here for Q2's best response, this becomes 2 minus 1/2 times 4/3, or 2 minus 2/3, which is also 4/3. So Q2 is equal to 4/3 as well. Right. And then big Q, or market quantity, is Q1 plus Q2, which is equal to 8/3. And then the price is equal to 12 minus 2Q, okay, which is 12 minus 8/3, or 16/3. Which is basically 36 minus 16/3, or 20/3. All right, so now I'm going to talk about the N-firm case and nested benchmarks, and that's basically pages 4 through 6 of lecture 13. And really there's sort of, I guess, two takeaways that I want to make. And they're related. So one, Cournot limits to perfect competition and monopoly. And then two, basically I want us to get a better sense for how we see the effects of competition. So last time I was much more focused on showing the math. This time we're not going to be required to know the math, so let me actually write that down. Math is not required. As in, like, I don't require you to know it. But I think it's really useful to get the intuition here, and so I'm gonna do a little bit more time focusing on that. The math is going to be pretty similar. We're just going to have more than one or more than two firms. All right. So the setup here, we have n greater than one firm selling a homogeneous product. We're going to have the same demand curve as lecture 3.2, 5 minus q, right, where now q is equal to q1 plus q2 plus dot 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 all the way to qn. And we're going to have the same cost curve, cq is equal to 2q. All right. So the goal is to find the equilibrium price and quantity. All right. And we're going to do that the same way that we did before. So first we're going to find firm 1's best response as a function of all the other firms' quantities. And we're going to do that the same way we did before, which is let's write down the profit function for firm 1. Right? In this case, it's 5 minus Q1 plus Q2, right? The market quantity. And all of that times Q1, right? So this is going to be the price once we know what these quantities are. This is the amount that firm 1 produces, right? Minus 2Q1. If you do the algebra on this, so this is going to be 5Q1 minus Q1 squared minus Q1 times Q2 minus dot 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 minus Q1 times Qn minus 2Q1. All right, and then we're going to take the first order condition as we had doing. I'm doing the same steps that we did before. I just have all of these other Q's floating around. And this is going to lead us to 3. I'm just doing the 5 minus 2 here. Minus 2Q1 minus Q2 plus dot 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 Qn. And we're going to set that equal to 0. All right. And then we're going to solve for Qi as we have been. Zoom in a little bit here. And what we're going to get, we can add Qi to both sides, divide by 2. And we're going to get, Q1 but by both sides divide by 2 or multiply by 1/2. And we're going to get Q1 is equal to 3 minus basically Q2 plus dot 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 Qn. All right, and this is firm 1's best response function. All right, and then imposing symmetry. right, we can say that Qi is equal to 1/2 times 3 minus, so this is their n minus 1 Q's here, n minus 1 Qi, okay, by symmetry. Now to solve for firm 1, right, so to solve for Qi then, right, all we have to do is multiply both sides by 2. So we get, or it's easier, I guess, if we do that. So we get 2Qi is equal to 3 minus n minus 1 times Qi. Let's add n minus 1 to both sides, and we get n plus 1, right, times Qi, because we had 2 Qi's here, right? We add n minus 1 to both sides, we get n plus 1 is equal to 3, or Qi is equal to 3 over n plus 1. Okay, so this is firm I, any firm i's quantity in a Nash equilibrium. All right, and what I said, right, the first takeaway here, right, Cournot limits to perfect competition in monopoly. So let me show that. So I'm going to nested benchmarks. All right. So with monopoly, the way that we're going to get this is we're going to assume that n is equal to 1, right, with a monopolist. So Qi is equal to, and we're going to call this, I guess, Qim, right, or just Qi in this case. Using this value, we're just going to plug in 1 here, and we're going to get 3 over 2. And then the price, right, if the quantity is 3 over 2, right, using the demand curve, plugging 3 over 2 into 5 minus Q, right, is going to be equal to, well, 5 minus 1.5 is 3.5. All right, for perfect competition, that's going to be the case where n goes to infinity, right? We have lots and lots of firms, all right? So aggregate demand is equal to the number of firms times each firm's demand, or aggregate supply is equal to the number of firms times firm supply, right? Which is equal to 3n over n plus 1, right? So the limit as n goes to infinity of Q is going to be 3, it's just going to be 3. All right, and then the price at that limit quantity is 2, right? Because that's what it's going to take. That's the price, right, that's going to sell 3 units of output. All right, so in that sense, the Cournot model nests the monopoly and perfect competition benchmark. And to see that, like, remember in like lecture 13.2, right, we solved out for what the perfect competition and monopoly numbers should be, right? So we said that monopoly had a quantity of 1.5 and a price of 3.5, and that's what we find here, right, under Cournot, but with one firm. Right, with perfect competition, price is equal to marginal cost, which is 2. We found that, and the quantity that we found was 3. Okay. So first point, right, that makes right, is just, Cournot limits to these, perfect competition and monopoly. Why does that happen, or what is sort of happening underneath the hood? And so now I want to talk a little bit about sort of how competition is working in this case. So the first thing I guess that I want us to see here, right, is so there's sort of two examples that we've done. The first, when we had two firms, right, we had a best response function, which was Q1, this is in lecture 13.2, Q1 is 3 over 2 minus Q2 over 2, right? For like n firms, right, we had an equilibrium amount, which was like Qi is equal to 3 over n plus 1, all right? In both of these cases, right, if the other firms produce more, right, firm 1 will produce less. All right, so if Q2 is larger, Q1 is lower, right? And I make a big point of this in the Stackelberg model, which I'm not going to do this semester, right? But basically, if what firm 2 could do is produce a lot more than its equilibrium amount, right? It might want to do that because it's going to make firm 1 produce less, right? In the n firm case, if you have more firms, right, then firm 1 will produce less, right? So again, right, this is how competition is working, right? Other firms producing more leads this firm to produce less, right? If we think about like what's happening in like oil markets right now, right? All of the countries in OPEC are trying to decide that or trying to come to an agreement to produce less oil, right, in order to raise the price, right? But some firms want to produce more, right, which is going to lower the production that other firms should make, right? Well, it's also going to make other firms less profitable because it's going to lower the price and it's going to lower their quantities, right? So these firms are, by producing more, are basically placing an externality on the other firms, right? Saudi Arabia, if it produces more oil, right, creates an externality for producers in the U.S. or producers in Russia, okay? And what that implies then is that this is a prisoner's dilemma, right? Or this has sort of the feeling of a prisoner's dilemma. Right? So each firm is maximizing their own profit. Right, which is sort of necessary in a prisoner's dilemma, right? But their quantity, right, reduces profits for other firms. All right. Right, and so this is like an externality on other firms, and the issue, right, is that each firms don't internalize the full cost of increasing production. I should say the full price effect, just to be a little bit more careful here. Right, so in monopoly, right, the reason that a firm produced less, right, was because when it produced less, it had to sell each unit at a lower price. Sorry, if it produced more, right? If it produced like one more unit, right? Each unit that it sold had to be sold at a lower price. And so that's what stopped the monopolists, right, from producing a lot, right? Here, right, when a firm produces more, right, it does lower its own price, but it also lowers the amount that other firms produce, right? So it doesn't fully internalize that, but it makes it, you know, one, it hurts the profits of other firms, but also it reduces the production of other firms, right? And so it isn't fully facing the full cost or the full price effect of its own extra production, right? And because it's not facing that, right, firms are going to overproduce compared to the monopolist, and so they're not going to be as profitable. Like the Cournot competition model is not as profitable as the monopolist model, even in N, right? Even if you add up. So in the limit, which is perfect competition, right, firms produce all the way down to prices equal to marginal cost, and they're producing that amount because they don't really internalize the cost of increasing production, right? Most of that cost is borne by the other firms, right? And so they want to increase production, which gets us all the way down to price is equal to marginal cost. You wouldn't produce more at that point. But that's sort of the sense in which this is a prisoner's dilemma, right? Each firm is trying to maximize their own profit, and by doing so, they're actually diminishing the total amount of profit in the market. This turns out is probably very good for consumers because it reduces deadweight loss. But right now, when I'm saying, like, you know, this is a suboptimal outcome, it's a suboptimal outcome for the firms, right? They should do what OPEC does, which is all agree that they're going to produce less output, right, in order to get more profit. But they can't do it in the same way that, you know, you all would have a really hard time on GroupMe deciding that you're not going to study for my final, right? And so because they can't coordinate on lower output, right? Because each firm has the incentive to maximize their own profit, you know, in the limit, they will, you know, as the number of firms gets large, right, we'll get back to perfect competition. All right, so now let's talk about Bertrand competition, which is lecture 13, pages 7 through 10. And the idea of Bertrand competition, or you know, Bertrand, I guess, started off by sort of criticizing the assumption that firms compete on quantity. I mean, that might be true in some markets, but probably not in all. And so he was thinking about firms competing in price. And the crucial assumption here is homogeneous products right? Which then implies, as you know, we talked about at the beginning of the perfect competition lecture, right? What that implies, right, is that if a good is like 1 cent cheaper, right, all of the consumers, right, will choose the cheaper good. All right. Now, and basically the takeaway here is going to be that Bertrand competition immediately, it immediately competes away any markup, right? So while it may feel more realistic to have firms competing on price rather than quantity, or more natural to do so, right? The takeaway that I want you to get from this is the outcome of the model doesn't feel very realistic. right? Now it may, under the actual assumption of perfectly homogeneous products, work well, but we'll talk about in the next lecture that, you know, for a lot of products that are not perfectly homogeneous, and that can just mean, you know, differentiated by location. So maybe, you know, you have 2 gas stations and one is across the street, you'd rather pay an extra cent a gallon, right, to go to the one closer to you, right? In that case, we're sort of breaking the assumption of homogeneous products. So maybe it is realistic for homogeneous products, but for a lot of situations, maybe that's a really strong assumption that that products are homogeneous. I also want to make the point that it's probably in some settings Cournot competition is reasonable, like, you know, corn or oil or things like that, you know, commodities, and some, right, we might think that, you know, price competition is more reasonable. So I'm not saying that, you know, this assumption is always better or always worse. It depends on the industry, and it depends on how well we think the market is really homogeneous. Okay, so I'm going to start with the example of identical costs. Okay. All right, and the punchline is going to be that firms price at marginal cost. All right, so let's suppose that we have 2 firms. And for each firm, C of Q, let's say, is equal to 2, or 2Q. And each firm, basically the way that demand works, right, is whichever firm is cheaper, right, gets all the demand. Whichever firm is more expensive gets no demand. If the prices are the same, all right, then they split the market. Okay, so the question here asks us to find Nash equilibrium prices, P1B and P2B. All right, and I'm going to argue just sort of right away, where I'm going to propose the equilibrium, and this is sort of, I know where we're going. Is P1B is equal to 2, P2B is equal to 2. All right, and that's because marginal cost is equal to 2. All right, so let's think about this for a moment. Suppose that one firm, say, priced at the, you know, let's just say, right, that firm, you know, 2 set a price of 3. Right, what's firm 1's best response? Right, well, firm 1's best response is to price at $2.99. Okay, but then firm 2's best response is $2.98, and firm 1's best response would then be $2.97, right, and so on and so forth. And so you can see at no price here, right, is there a Nash equilibrium that's above 2, right, because it's always going to be more profitable for the firm to undercut by 1 cent, right, in order to capture the entire market. And that's also, because it captures the entire market, right, it's going to be the most profitable price to sell at. Right, it wouldn't want to, go, the best response to 298 isn't, to 299 isn't 297, it's 298, right, because it wants to capture the whole market. And so we're going to go all the way down to 2. So let's say that firm 1 prices at 2, right? What's firm 2's best response, right? So if it prices at 2, well, okay, let's say that firm 1, yeah, prices at 2.00000001, right? Firm 2's best response is to undercut that by just a little bit, right, in order to get all of the market and that like little fraction of a cent of markup, right? If we're limiting ourselves to whole number, you know, cents, let's say, right? We could think of this as being like firm 1 should price at $2.01, right? If firm 2 prices at $2.01, right, they both get 1 cent of markup for half of the market. Okay. So this here, right, each firm pricing at $2.01, right, each firm gets half a unit of profit, right? If firm 2 raises its price, right, to $2.02, right, it gets no profit. If it lowers its price to $2, it gets no profit. So it's playing a best response to firm 1. Firm 1 likewise is playing a best response to firm 2, right? If it raises its price to $2.02, it gets no profit. If it lowers its price to $2, it gets no profit. So when I say it prices at exactly marginal cost, right, it prices slightly above marginal cost, but like in the limit, if we didn't have sort of cent constraints, right, it would it would make its way all the way down to marginal cost. Okay. So the takeaway, right, with identical cost, firms price at marginal cost. I do want to highlight that we use this price competition example for both dominant strategies, right? There was no dominant strategy because firms, it was never like always the best thing to price at $2.99 or to price at $2.01, right? So there was no dominant strategy and there were no dominated strategies, right? Any strategy, you know, if I want to price at $2.98, right, that's a best response to pricing at the other firm pricing at $2.99, right? And so there were iterated elimination of dominated strategies, didn't get rid of any prices. The dominant strategy equilibria, there was none, right? But we do actually have a Nash equilibrium in prices in the Bertrand game. So that's sort of the advantage of, you know, one of the advantages of the Nash equilibria. We actually do get a pretty stark result here, and one that I think is pretty intuitive once you sort of think about what it means to have homogeneous products. Okay, so while very intuitive is a little bit, it's a little bit scary, right? Because we shouldn't necessarily think that, you know, firms make profit in real life, right? We see, you know, there's a whole major called accounting that like adds these things up, right? It's weird that, you know, we think firms are competing on price, but then we don't see profits come out. So there are a few ways to get around this. One way is that, well, what happens if firms have different costs? All right, so that's going to be example Bertrand with different costs. All right, and so let's say that firm 1 has a cost function of Q1 5 Q1, and firm 2 has a cost function of 6 Q2. All right. Demand works the same way, where basically whichever firm is cheaper gets all of the demand. And then again, find the Nash equilibrium prices, P1 star and P2 star. All right, and so again, right, let's just think carefully about what we think should happen here. Right, so suppose, so I'm just gonna propose, right, that the Nash equilibrium here is that firm 1 should price it like $5.99, and firm 2 should price it exactly $6. Okay, So let's suppose that wasn't the case, right? So let's say that, like, you know, firm 1 was pricing at, and this is going to wind up being true, but suppose that wasn't, so let's say firm 1 priced above $6, so let's say, you know, priced at $6.50, right? Firm 2 would price at $6.49. Firm 1 would then price at $6.48, and we work our way all the way down to 6, right, without finding a best response. Once firm 2 is pricing at 6, right, firm 1's best response is to price at $5.99. Now, firm 2 can't price at $5.98, right, because that's below cost, right? So firm 2 shouldn't price below 6, and so firm 2 is stuck at pricing at 6. Firm 1, you know, then can get the entire demand by pricing at $5.99. Firm 1 wouldn't want to price below $5.99, right, because then it's just losing profit, right? If it were to price at like $5.75, right, firm 2 is still going to price at 6, and firm 1 is just throwing away revenue at that point. Okay. So it should price, so the equilibrium has to be that firm 1, right, it doesn't want to price any lower than $5.99. If it prices above $5.99, right, it's going to get undercut by firm 2. So this is a best response, and firm 2 basically can't price lower than 6, right? And, you know, pricing above 6 doesn't really matter for it when firm 1 is pricing at $5.99, and so it's playing a best response, and so they're basically playing best responses to each other's best responses. Hence, this is a Nash equilibrium. Okay. So, in terms of takeaways from sort of these two games, so this is referred to as the Bertrand paradox. So going from, and what we mean here, right, is going from monopoly, or just one firm, to duopoly, so two firms, right, leads to either both firms price at exactly marginal cost, and make no profit, right? So in Cournot we saw, like, we went from one firm to an infinite number of firms, and we got from, you know, one firm, we have the monopoly outcome, to infinite number of firms producing at exactly marginal cost and making no profit. With Bertrand competition, that's one firm to two firms. Or, right, we get the case where only the firm with lower costs produces, and, you know, they set a price at the next cheapest firm's marginal cost. Right, and I think the issue here, right, is that neither of these seem like very realistic, right? If you watch like CNBC for like 30 seconds, right, you'll realize that, you know, firms are charging different prices, firms are very profitable. You know, it doesn't take long to look at this and say, wait, you know, this is a really intuitive, model, right? It seems like a really nice way to set up price competition. Right, but the point here is that it doesn't like work very well, and it gives very extreme outcomes that we don't think are very realistic, and so maybe it's not sort of the best model. As an undergrad, like I think you just need to know what is meant by Bertrand competition and what's sort of meant by the Bertrand paradox. So this is sort of the really, really important takeaway part of this. I'm going to talk about now one more example that I want you to know how to work with, which is Bertrand with capacity constraints, and then I'll do hotelling, which are basically two ways of breaking the Bertrand paradox. And you won't be responsible for the next, for the hotelling model, and that's in the next video. So this is more of a, if you're curious and you don't like the fact that I'm leaving, you know, this entire semester class on a paradox, I won't. But if you're just, you know, sort of fed up with this or really busy, just pay attention to the capacity constraints part of this, right? So here, I want to talk about Bertrand with capacity constraints. And I should just say, as I'm working through this, one way to do this is you add capacity constraints, and you'll see why that fixes the Bertrand paradox. The other way is just to assume that products are differentiated, right? So in a world where people have taste for certain things, there's some ability to charge a markup because not all of the demand is going to leave immediately. Okay, so in this example, the Bertrand with capacity constraints example, we have a demand curve, PDQ is equal to 5 minus Q. So this is the one we've been working with quite a bit. We have marginal cost is equal to 2, all right? But let's say now that each firm can only produce 1 unit of output. So Q1 bar is equal to Q2 bar is equal to 1, all right? And I just want to make the point, actually, because I think this is an interesting point to make. This is the same output as our Cornot example. Okay, so we want to find the equilibrium price in quantity. All right, so let's start off, right, and just think about, well, what happens if each firm produces its entire capacity, okay? So if each firm produces its entire capacity, right, then we have Q is equal to Q1 plus Q2 is equal to 2, right? And then plugging this into the inverse demand curve, P of Q is equal to 5 minus 2, which is equal to 3. Okay, so let's suppose right now, right, let's propose an equilibrium price of 3. All right, so P1 is equal to 3 and P2 is equal to 3 as a Bertrand price. All right, is this an equilibrium price, right? Is each firm playing a best response to the other firm's, best response, right? So let's think first about, should firm 1 lower its price? Right. So let's say that it charged like, I don't know, $2.95. Right. Well, what's going to happen here, right, is that firm 1 will sell its full unit of demand, right? And then firm 2, right, can still sell firm 1 can sell its full unit, right, and get $2.95 of revenue. Right? And so it's lost money, right? It's already selling its full unit, right? So why charge a lower price? It can't produce more, right? Now, suppose both firms set a price of like $3.50, right? Or firm 1 sets a price of $3.50. Okay. So firm 1 is pricing above 3. Firm 2, let's say, is still pricing at 3. What happens? Right? Well, firm 2, right, will still sell its unit. Okay. And therefore, right, our inverse demand curve, or the demand curve facing firm 1 is going to shift in, right, to be basically, right, 5 minus 1 minus Q1 right, or 4 minus Q1, right? But now, right, if the price is $3.50, the firm 1 can't sell, right, its full unit at $3.50, right? It can only sell half a unit at $3.50, right? And so firm 1 should lower its price. Right, because it cannot sell right, so its new revenue would be $3.50 times 0.5, which is 1.75. That's much worse than its old revenue of producing 1 unit and getting $3 for it, right? So it should lower its price. So the point being, right, that if one or both firms has a price above $3, right, they're not going to sell the 2 units, right? And so lowering price brings us back into the world where these pricing above $3, right, and having the capacity constraints here, right, brings us back into the world of Bertrand competition where they need to lower their price again and again and again in order to sell all of their output. Okay. So there are 3 takeaways from this, right, that I want us to sort of get, and I'm going to write each one down, and then I'll talk about them more as I go. So 1, right, the reason for the Bertrand paradox, is each firm faces an infinitely elastic demand curve, right? And the firm faces that, right? So it didn't need to be that the market demand was infinitely elastic, right? Just the firm itself is facing an infinitely elastic demand curve. The idea there, right, is, you know, what's doing this, right, is the product homogeneity, right? If products are identical, right, then raising your price by 1 cent causes everybody to leave, right? It may be that there is like a broader demand curve for like corn, right, but charging 1 cent more than, you know, the guy next to you at the farmer's market is going to cause everyone to leave. So you as a firm are facing an infinitely elastic demand curve, which is why you can't price above marginal cost or price above what your neighbor is doing. Right, and so I think it's important just to think about, you know, each firm demand curve being infinitely elastic, and that's really what the, you know, the product homogeneity assumption is doing. That's why we get that in perfect competition. Like that's what, you know, I'm sort of drawing back to, you know, lecture 9 in perfect competition there, and I think this is sort of an important point for both that and Bertrand. The second point that I want to make, right, is under the capacity constraint, right, or under Cournot competition, right, we can think of firms no longer facing an infinitely elastic demand, but rather firms face or act as monopolists against the residual, what's called a residual demand curve. Okay, so what I did in the capacity constraint model, right, is I subtracted out the, you know, the one unit that other firm, you know, that firm 2 produced, and then we could have thought of firm 1 as basically optimizing, you know, under the capacity constraint. In the same way, right, with Cournot, right, we sort of figure out what the other firm is going to do, right, and then we can come back and basically write down the profit function for firm 1, right, given what all the other firms are going to do, and then maximize profit in the same way that you would for a monopolist. Okay. The issue, though, right, is those other firms are producing something, right, and so it's not that, you know, we can think of firm 1 as a monopolist, right, but rather it's a monopolist once we've gotten rid of, you know, what the other firms produce, right. The issue with Cournot, right, is that what the other firms produce is a function of what they think you will produce, and that's sort of where the game comes out. Right? With the capacity constraint, right, the idea is that the other firms are limited to their capacity, right, and so the residual demand curve is less of a game and more just these firms will produce a certain amount. But once we sort of got rid of that, we can just think of, you know, firm 1 acting like a monopolist, working against, you know, a demand curve, right, where we've netted out the fact that firm 1 is going to sell everything that or firm 2 is going to sell everything that produces. And sort of the final point that I want to make here, right, is when quantity is fixed, then the demand curve tells us the price which clears the market. All right. So in the capacity constrained world, right, firms produce 2 units of output, right? And then we knew exactly what the price was because we just said, well, what's going to sell 2 units of output? Right? In the Cournot competition world, right, firms produce a certain amount of output, and then the price is exactly what the demand curve tells us. In monopoly world, right, what we did is we found the monopolist quantity where marginal revenue is equal to marginal cost, and then we walked up to the demand curve to tell us the price, right? So in all of these models, right, what we're doing is we're finding a quantity and then saying, well, what's the price that sells all of this quantity? What's the price that clears the market, right? And to do that, we just go up. We just plug that into the demand curve to figure out basically, you know, at what price will the demand be enough to clear the market. So anyway, this is the last of the material that you were responsible for. I'm going to add one more lecture on the hoteling model because I think it's a more realistic model for price competition, and it's really sort of the basis of what actually gets used in sort of cutting edge research nowadays. And so I think it's an interesting thing. But if you don't, you know, if you don't want to, you don't have to. If you do, you know, please follow along for one more lecture. But I hope you enjoyed the class. It just feels like it would be sort of a disappointing or sort of a letdown of an ending, given, you know, sort of the story of the class to finish this on, well, we don't really know. So that's what I want to talk about, hoteling. So the issue with Bertrand is that product homogeneity is a really strong assumption. You know, the idea that for just 1 cent, all of the demand would leave a firm, right? Or, you know, firms basically face infinitely elastic demand. Seems unlikely in real life. So I think when I was talking about this, I talked about, you know, would you be willing to pay 10 cents to cross the street to go to a gas station? And sometimes it seems people are, right? But more generally, I mean, there's lots of ways in which firms differentiate themselves, right? So we could think about, you know, say differentiation in product quality. So, you know, Zaxby versus Chick-fil-A. Downtown, like there are differences in the chicken, and some people might be willing to pay more to go to Chick-fil-A, or some people might be willing to pay more to go to Zaxby, right? And because of that, you know, Zaxby can charge a higher price than, you know, marginal cost because they can get people who like their chicken better. Also, just like locationally, they are different, right? You know, you got to walk 2 blocks further from campus to get to Zaxby than Chick-fil-A if you're thinking about the Chick-fil-A on Broad, right? And some people just may not be willing to do that. And so, again, I mean, that's going to allow Chick-fil-A to charge a slightly higher price because some people won't walk further to get, you know, maybe Zaxby at a lower price even if they were the same good, right? So there are lots of ways that we can think about product differentiation. And if products are differentiated, right, then firms no longer face an infinitely elastic demand curve. Right? If Zaxby were to raise its price by 1 cent, it's not like all of its consumers are going to go to Chick-fil-A or vice versa, right? They have some, I mean, if they were to raise their price by 1 cent, maybe a few people would leave, right? But not everybody. And why not? If you think about it, like, is it really worth that much to you to, walk those 2 blocks, right? I'm usually the type who's like pretty happy to walk and pretty cheap. Um, but like for 1 cent, I don't know that I would take the time, right? And so this then allows firms to act a little bit more like monopolists facing a residual demand curve. Obviously, if Chick-fil-A lowers their price, right, that's going to hurt the demand for Zaxby, but only to some extent, right? And Zaxby still has some ability to mark up their price, even if sort of their demand is diminishing as they go. So the idea then is we want to model product differentiation. And the way that we're going to do this is we're going to model it as though it's physical space. Fancy economists will model something that we call product space. As being similar to physical space. So what we'll do is, we can think of, the characteristics of, of like a product, like, how much do we like the taste of Zaxby? What are the health characteristics? What are the, how good is the dining experience? Where is it located? All of that we can sort of think of as product space, or just like the characteristics of, how much we like that product, right? And we can model that sort of abstractly as, how close are certain consumers to one product or the other? How much do they like Zaxby versus Chick-fil-A, right? So in practice, the way that we're going to do this is, and there are more complicated models of this, but I think this is a nice sort of straightforward way to model this and at least show you how we solve this Bertrand paradox problem. So we can think of there being like a linear city, is what it's called, and there are 2 firms. So there's a firm at location 1, and there's a firm at location 0. All right, and they both sell some product. I'm just going to keep calling this chicken, but and consumers are willing to pay $2 for that product. Like if they were at the store, they would pay $2, and for each one, right? So if they're here, they're willing to pay 2. If they're here, they're willing to pay 2. And otherwise, products are homogeneous. So this is the location of the stores is the only way that these products are differentiated. So everything that comes out of differentiation is coming from this part of the model, okay? And then stores are going to charge prices P0 and P1 respectively. And these are going to be equilibrium objects. So we're going to have to solve out for what these prices are. We're going to denote a consumer's location by X. Right. And we're going to assume, just to make life easy, that consumers are uniformly distributed across the city. All right, so what this means, like, let's say that we're looking at a person at x is equal to 0.25, right? What this means is that, or what the uniform distribution buys us, is that we know that a quarter of the population, right, is between that consumer and 0, and 3/4 of the population is between that consumer and 1. Right? If we were to consider the consumer at, say, 0.5, right, we know half the population is on this side of the consumer and half the population is on that side of the consumer. And like, we use much more complicated distributions than this, but for the sake of this class, let's just use a uniform distribution. And then there's going to be some travel cost, which I'm going to denote by t. And that like is going to help us to think about, well, what happens when the cost of traveling changes, right? So if it was free to travel to get from one to the other, we could think about that as sort of shrinking the distance, right? Like if you really didn't mind walking, it was a gorgeous day out, the travel cost from Zaxby to Chick-fil-A might be very low, in which case, you're much more sensitive to like Zaxby cutting a price. If you're at, if you're at the Arch and Zaxby has a $1 lower price, you might be willing to walk for it. If it's like a major rainstorm, right, you might not be willing to walk that extra block for Zaxby, even if they were like $10 cheaper. So the travel cost here is going to tell us something about, it's going to help drive demand, or the elasticity of demand. And then finally, we're just going to say 0 production costs. So it's free for the firms to make the chicken. All right. So the way that we solve this game, and especially because of the linear city, it's just sort of one dimension of differentiation. We can look for the indifferent consumer, right? And then know that everybody to the left of that indifferent consumer, right, is going to go to firm 0, and everybody to the right is going to go to firm 1, because everybody to the right has lower travel cost to firm 1 and higher travel cost to firm 0, and everybody to the left has lower travel cost to firm 0 and higher travel cost to firm 1. Okay, so we can write down the utility for consumer 0 as 2 minus t times x, so 2 here is their willingness to pay for the chicken, minus t times x, which is the travel cost times their location and how far they are from 0, minus the equilibrium price P0. And for the utility for consumer 1 is 2, which is their valuation of the chicken, minus T1 minus X, right, where now their distance, say from firm 1, right, if you're at 0.25, right, your distance is 0.75, okay? Your distance from 0 is 0.25, your distance from 1 is 0.75 minus P1, right? And our goal is to find equilibrium prices. P0 and P1. And to do that, like I said, we're going to find our indifferent consumer. Right, so we're going to set U0 equal to U1 and solve for X. All right, so setting U0 equal to U1, we get 2 minus Tx minus P0 is equal to 2 minus T. I'm going to distribute this, so minus T plus Tx minus P1. And we're solving for x, so let's add Tx to both sides and subtract all of this from both sides. So we're going to subtract the 2's and they're going to cancel. we're going to add P1 to both sides and add T to both sides. And so we're going to get P1 minus P0 plus T is equal to 2Tx. We're solving for x, so let's divide both sides by 2t, and we're going to get x is equal to 1/2. That's t over 2t, plus p1 minus p0 over 2t. All right, so this is our indifferent consumer. Right. As travel costs get big, right, the indifferent consumer is going to go more and more towards 1/2, right? Just basically, which one do they not want to travel further for, right? Or which one is closer to them, right? If travel costs are big, they don't want to travel, and the prices aren't going to matter very much. If travel costs get small, right, the difference in the prices is going to matter. Right, and the consumer will go then to whichever is cheaper if this thing gets, you know, pretty small. Right, which is intuitive, right? If travel costs are small, maybe that means that it's a nice day out and they're willing to walk like pretty far for you know, to get the lower price, considering that they otherwise like the products equal. Right, though again, travel costs here could be just I have a taste for, you know, I want pizza, and so I'd rather go to Little Italy than, you know, Chick-fil-A or something. Or I mean, that's sort of what the distance tells us. Okay, so we now know the indifferent consumer. Now let's figure out what demand is, right? And this is where having a uniform distribution really helps. Right, because if we know our indifferent consumer, let's say, is, you know, at 0.25, we know exactly how many people are going to go to firm 0. It's everyone below x. Okay, so demand for firm 0 is exactly x, right? Because that's just all the people to the left of this indifferent consumer, and that's, you know, it's just this minus 0, which is x. And so demand for firm 0 is equal to 1/2 plus P1 minus P0 over 2T, right? This is exactly X. And then demand for firm 1 is just equal to 1 minus the demand for firm 0. All right, which is equal to 1/2 plus P0 minus P1 over 2T. All right, so all we do when we subtract 1/2 1 minus 1/2 is just equal to 1/2, and then we would have a negative sign here, right? But that just flips, you know, the P0 and P1. Right. So these are our demand curves given our uniform city. And now let's just solve out for the firm's best response function. Okay, so and we're going to do that in the usual way, which is let's write down the profit function and then take a first order condition. So profit for firm 0, right, is equal to now P0 minus the cost, which is going to be 0, right, times their demand. Right, if we were to distribute this, right, price times quantity minus cost times quantity, the costs are 0, And so what this is going to simplify to is P0 times the demand curve, which we just solved out for, which is 1/2 plus P1 minus P0 over 2t. Taking the first order condition, right, this is going to become 1/2 plus P1 over 2t, right, minus 2P0 over 2t, because we have a P0 squared here, but the 2's cancel, and so we get something like this. And then solving for P0, we're going to set that equal to 0. Solving for P0, we get P0 is equal to t times 1/2 minus P1 over 2. Okay, and just because of symmetry, we can also get P1's best response function. So P1 is equal to t times 1/2 minus P0 over 2. All right. Sorry, and these should be, I'm doing bad math here, these should be pluses, right? What this tells us, okay, is that as the travel cost gets higher, right, the firms can raise their prices, right? So if it's a bad day out, right, Chick-fil-A can charge a higher price because you're less likely to want to walk to Zaxby, right? So that's intuitive. And then if the other firm charges a higher price, right, this firm can charge a higher price, right? So if Zaxby charges a higher price, then so can Chick-fil-A. You don't have a choice. All right. And so if we're going to plug these values in for each other, we would get P0 is equal to t over 2 plus 1/2 times P1, which is t over 2 plus P0 over 2. And you can go through the math of this, but what we should get here is that P0 is equal to t. Okay, and then P1 is equal to t. If you just go through the algebra, and that's in the notes. So the thing that I want you to see here, right, is that the Bertrand paradox has disappeared. Right, marginal cost is 0, right, but firms can charge a higher price. Right, if travel costs are large, right, firms can charge a price well above marginal cost, well above 0. So this gets us, away from that particular problem, right? But note that if travel costs are 0, so it's still like firm, you can go, if travel costs are 0, so like, we think that Zaxby is right next, or Chick-fil-A on campus is right next to Chick-fil-A on Broad, right? So we have two exact same products, right? Then yeah, we're back into this world of Bertrand where firms can't price above marginal cost, right? But the instant that travel costs rise, either because the products get more differentiated, like, we're thinking about Little Italy competing with Chick-fil-A, or just products get further apart, like actual physical product space, right? Then firms have to pay, or then consumers or firms are able to charge above marginal cost and therefore get some markup. So again, I think that, this is just what I wanted to do here was just show that we can get out of the Bertrand paradox by thinking about firms being differentiated. And just, this is one way to do it. And I think a very intuitive way to do it is just, thinking about, the reason that I'm willing to pay more for something is because I like it more. And by creating some differentiation, right, that is allowing firms to actually get some markup, because I'm not going to instantly switch to their competitor if they raise price by $1. Anyway, for those of you who watched this, I hope this was interesting. This is a little bit closer to sort of cutting edge how we model product differentiation and price formation.